Welcome back to the course in Nuclear Medicine Physics. Today we're looking at various types of data correction that need to be done after you gather your data from detectors in PET imaging. Like in SPECT, not all the photons that are emitted from the patient reach the scanner. A lot of them get attenuated by the muscle and bone of the patient. In regions of the body that attenuate more, proportionally you're not going to see as much radiation. Another major issue with PET is random detection. For example, you might have two photons that are emitted back to back here, and another place two photons that are emitted back to back. And it just so works that one photon from one pair and one photon from another pair get detected at the same time. This gives us an incorrect line of response of where the photons came from. There's also things like scatter as well, where two photons get emitted and maybe one scatters, so you have them going like this, and then this goes like this. And that also gives us the wrong line of response of where the photons came from.
All right, so we're continuing with our discussions on the science and art of PET imaging. And in this fourth short lecture, we're going to be talking about data corrections. We would like to have really reliable images that give us superb image quality and also move us to the domain of quantitative imaging. So to do that, we're going to have to consider a number of degrading phenomena in PET. So what are those degrading phenomena in PET, and how can we compensate for them? So basically, I'm going to go over 8 different phenomena in these 2 upcoming lectures. The one right now, the first 4, and then the next one for the next 4. So the first 4 I'm going to talk about in this lecture are the attenuation of annihilation photons, detection of scattered events, detection of random events, and dead time. So all these things degrade image quality and or quantitation in PET imaging, and so we need to compensate for them. There's also variations in detector pair sensitivity, so we need to do some kind of a normalization. Decay of radioactivity needs to be taken into account. And then if you're correcting for all of these, there still remains other things that degrade resolution. Now, scattered and random events also degrade resolution, but let's say we've corrected for them. There still remains other things that are degrading image resolution, such as detector blaring, like intercrystal scattering, things of the sort, positron range, which is unique to PET and not single photon imaging, photon non-collinearity, which is something we're going to talk about, this interesting phenomenon, and finally, patient motion. So we're going to try to cover these 8. As I mentioned, the first 4 in this lecture and the next 4 in the next one. So what's a true coincidence? A true coincidence sort of has to have a number of it has a number of requirements, really about 3 of them. That both photons from an annihilation event, so this is where a positron and an electron have annihilated, giving you the 2 anti-parallel gamma rays that is the foundation of PET imaging. Both of them are detected, okay? And neither has undergone any kind of interaction prior to detection, like they haven't scattered or things like of the sort. And no other event, like another event coming from up here or down here, is detected within the coincidence time window. So just a clean, event. So that's the true coincidence. But let's now talk about these other things in comparison to that. So attenuation. Well, attenuation is the largest degrading contribution in PET imaging. It happens when one of the annihilation photons is not detected. It could be 2 also, right? But at least one of the annihilation photons is not detected. Now, it could be absorbed, but we don't really have that in PET imaging because, as we've talked about before, in single photon imaging, at those lower energies, we can have the photoelectric effect in like soft tissue and in bones. But at 511 keV, we don't really have photoelectric interactions in the human body. So that's not really a factor, but it's really scattering them. So the reason 511 keV photons attenuate in the body is because they scatter away. and they don't end up where they were supposed to be detected. So notice how there's two photons along the line of response, and both of them have to make it to the detector. So if one of them is lost, if any one of them is lost, the event has not survived. Okay, so imagine you've got a source here. You got one photon going this way, one photon going that way. Well, both have to survive. Okay, so in order for both to survive, you have to have this probability, and this is a probability of survival going this way, that an event is not attenuated, that it survives, that it passes through this medium. Let's say this is water, soft tissue, or any kind of tissue. And then this is the other event. Both of them have to make it. But the beauty of this is that the overall probability of detection of survival of an event, here the X's go away. This term is independent of where your event is. All it depends on is this total path length. For this entirety of event, for this annihilation event to be detected, meaning both photons are detected, you only need to know this path length of attenuation. You don't need to know where the source is within that line of response. And that's one of the beauties and simplistic aspect or simple aspects in PET imaging. That is not true for single photon imaging. So this ends up actually giving you an easy correction. So we're going to see that in a while. Let's ask you guys a question here. How much attenuation occurs? Imagine like a 30 centimeter of soft tissue. And here's a mu value, attenuation value, in water. And soft tissue and water are taken to be almost the same thing in terms of attenuation. For 511 kV gamma rays, this is what we have. I often actually estimate this number to just be 0.1 in quick calculations. I have that memorized. 511 kV in water or soft tissue is around 0.1. So how much is going to be the attenuation? Not the survival. How much, what fraction, what percent of events will be attenuated, will not be detected? So let's enter your answers, please. And we sort of had a related question to this in the context of single photon imaging in the midterm. But here the question is for PET. And again, I have this number sort of memorized as 0.1 in my mind for quick calculations. Like sometimes when I think about the brain, I tend to think of it as like 10 centimeters. So, you're having 0.1 times 10 centimeters. That's a 1 in the exponent, so e to the power of -1. So it's about 30% of events sort of survive, and about 2/3 are attenuated in the brain. But if you're looking at the body and sort of taking this really simplistic number, yeah, so the numbers are coming in, and so the majority, most of the votes go to D, and that is correct. So this is essentially what you do. Again, this is a probability of survival of the event not being attenuated. So 1 minus that is going to give you that. So it's about 95%. So that's kind of interesting, right? So, and it's almost at first hard to believe. Out of every 20 events, 19 are attenuated. So a lot of signal is being lost because of attenuation. It's a significant number because, again, both photons have to make it across this distance. So that's something to think about. Now let's look at another interesting scenario where we try to compare numbers, get some intuition for PET versus single photon imaging. So again, just simplifying things to soft tissue only, just taking this 30 centimeters of soft tissue, sort of thinking about the body. So this is a number we already had. And then for technetium 99M imaging, where we have 140 kV, the attenuation is a bit more. because the signal is less energetic, so it does attenuate somewhat more in water or in soft tissue. So the question is true or false? There is more attenuation for PET compared to single photon imaging. Now, the catch is, think of single photon as 10 centimeter only. I should really emphasize this. You have a single event, a single photon coming, so the depth does matter in single photon imaging. So assume that your detector is somewhat close to the source, and the source is maybe here, right? So maybe the source is only 10 centimeters from here. There is no other event to survive. So it's only 10 centimeters for single photon imaging to go through. Whereas in PET, it's on both sides, so it's 30 centimeters. But the mu value is higher for this lower energy photon, whereas the mu value is lower for this. So what do you think? So do we get more attenuation? This is a very oversimplified example. Essentially, I'm trying to arrive at the question whether you get more attenuation in PET or, let's say, in single photon imaging, like in SPECT imaging. Very rough, back of the envelope sort of calculation. Okay, so so the answers are sort of split, and the answer is actually true. So why is that? So let's look at the numbers. So this is what we got in the last question already for PET, right? 95% of events are attenuated. But here, when you put in these numbers, first of all, the single photon only has to go through not the whole thing, but just let's say the organ of interest is somewhat close to this side. So let's say that's why you're putting your detector closer to it, as opposed to going from the back of the body. So only 10 centimeters. The attenuation length is the attenuation constant is a bit more, but it turns out that at the end of the day, you get less attenuation. So even though there is more attenuation happening, this is less energetic, so it does attenuate more, but at the end of the day, because it has to go through less amount of tissue, it only just has to go from here to here and not both ways, you end up attenuating less. So here, about, you lose 19 out of 20 events, whereas here, you lose maybe 3 out of 4 events. So that's sort of good to have those numbers in mind. So is this a big concern? Would you be saying, wow, in PET, we're losing more signal to attenuation, and maybe we shouldn't be doing PET imaging? That's totally not true, and here's the reason. Even though PET imaging can have larger attenuation, but please remember, sensitivity in PET imaging has already increased significantly since we have removed physical collimators. So if you're having just a standard, like a single camera, with collimators, now you can get rid of the collimators and surround the patient as you do with PET, and the sensitivity might have gone up by something like 2 orders of magnitude. So even if you're losing, let's say, you're gaining 2 orders of magnitude in sensitivity, even if your attenuation is somewhat more. So it's definitely not a concern in that sense. And also, it turns out that attenuation correction in PET is quite straightforward, even though you're losing signal, and that's not a great thing, but correction for it turns out to be quite easy. So a question we have is, what do you mean in SPECT it's just one way and in PET 2 ways? Remember, in SPECT imaging, you're doing single photon imaging. So you don't have 2 events that are going in. And let's just imagine that let's just think of this as the heart, and imagine that you only are designing your camera so that it goes only this way, because going around the patient only 180 degrees is sufficient. You don't have to do 360 degrees as we've talked about in the past. So just sort of going in this direction, and you only have single photon going through, you don't have 2 photons. In PET imaging, you have 2 photons, and that's a big difference, okay? But again, PET imaging, because it has 2 photons, opens up the ability to have much higher sensitivity because you do not have to do physical collimation, and you're accepting many photons from different angles because the other detector is telling you where they're coming from. And we talked about this in previous lectures. Okay, so because this attenuation, or the probability of survival, or being attenuated or not being attenuated, I guess the probability of being attenuated is 1 minus this term, is independent of where the event came from, and it just depends on this path length, and you just need to know where the detectors are and know the attenuation map in the body. It's very straightforward to correct for this. And in fact, that's one reason people used to say that SPECT is not quantitative. That is not a correct statement, as I've said before, because initially people didn't know how to correct for this phenomena in SPECT imaging, single photon imaging, because as you're reconstructing, you don't know what the source distribution is. You just know that you got a line here. You don't know where the event came from. So people didn't know how to correct for attenuation in SPECT. But later, as we discussed extensively in previous lectures, people figured it out. In a context of statistical iterative reconstruction, you can actually solve that problem. So SPECT is quantitative. But in PET, correction is far easier, far more intuitive. You just need to know the path length here, and you can calculate. Let's say you have a PET CT. The CT gives you the mu map, and you can just calculate the probability of attenuation. So there have been different methods to correct for attenuation. So measurement of attenuation has been done using transmission rods. We talked about that in the context of SPECT CT also, where you would have a source sort of rotate around, like a rod source rotate around the patient, kind of like a very slow and sort of poor way of doing CT. Whereas nowadays, in PET CT scanners, the CT does this only in order of a few seconds. So if you're projecting, let's say, along this circle here, you're supposed to get a profile like this. This is just a projection because there's more stuff happening here, more signal along this than there. You're supposed to get something like this, but in practice, you will get something like this because a lot of events are being lost here, attenuated here, but you can correct for that. You can figure that out using the attenuation map. And so you go from an image like this. This was not an image. This is an image, reconstructing image. You go from an image here where there's a big dip to a nicely reconstructed image that would be flat. Okay, so that's the discussion of attenuation. Let's talk about scattered events. So scattered events are, as is shown here, is one in which at least one of the detected photons has undergone at least one Compton scattering prior to detection. So this is the annihilation event. Here's the photon number 1, photon number 2. This was meant to be detected here, but I guess it was not meant to be detected here. It was scattered here, and it ended up being detected here. So please notice, this event has actually now been attenuated. This event was supposed to be detected, but it wasn't because there was scattering on the way to detection. So this event was lost, and that is attenuation and the need for attenuation correction. So this line of response, we have lost stuff, so we have to correct for it. But now suddenly we have gained a new line of response, and that new line of response is going to confuse the system because it's going to think, oh, wait a minute, I got an event here, I got an event here. I'm going to draw a line of response here, but that is not the correct line of response. So you've lost something here, so you have to do attenuation correction, but you've also gained something here. Now you have to subtract that or figure that out, get rid of that event. And sometimes when an event gets attenuated and scattered, the scattering signal may not be detected. But if it is detected, such as it is still within the energy window of the detector, it is still in the field of view, it hasn't left the scanner, it hasn't lost too much energy, because it loses too much energy, your energy window in the detector can get rid of energies that are too low. But if it's still within the energy window, let's say 511 keV plus or minus, let's say 10%, if it's still within the energy window and is detected, we get this misleading event. Okay. Yeah, so this will give us the wrong line of response, basically. And scattering sort of adds you somewhat of a background to the true coincidence distribution. It ends up, making your images sort of have lower contrast. There's this sort of background that is being added, and you end up, assuming you have corrected for attenuation, you end up overestimating things because there's these new events that you weren't expecting. And also they add noise. Why? Because, you know, anything we detect is a Poisson distributed kind of a thing. And even if you, so you're adding, even if you correct for it, still it was a noisy phenomena that was added. Even if you correct for it on average by a smooth scatter estimate, there still was the, you know, the noisy profile and signal of scattering that ended up adding noise to your signal. We will talk about this more in the context of, very important context of NECR curves, noise equivalent count rate. So we will talk about that later. And the number of scattered events, as you can imagine, depends on the volume of the subject. You know, the larger the object or subject being imaged, and the more attenuating media in it, like bone and things like that, obviously you're going to get more scattering. And also it depends on the geometry of the camera. So scatter correction is very important. And some, you know, people used to say scatter is the enemy because it was a difficult thing to correct for. And so here what you see is a small, let's say 30-degree scatter at the center of a typical scatter mispositions the event by 10 centimeters. And scattering is even more in the 3D acquisition mode, which we talked about before, when the septa are removed compared to the, you know, this older way of doing PET imaging 2D acquisition, which used to only give us maybe 15% scatter. Now in 3D, we're getting 40, 50% scatter. So scattering is becoming more, has become more, so it becomes even more important to correct for it. The advantage of 3D mode, as we mentioned, is that the sensitivity also goes up significantly. So it's a gain. It's good to switch to 3D because you're gaining more and more sensitivity, but you're also getting more scatter percentage, and you have to really correct for that. And correction for scatter is actually a challenging task. You know, people have spent careers on this. I think it's in a good place now in the PET imaging world. But the difficulty is that to technically estimate how much scattering you have, you need both the attenuation map, which is easy. You can get that, let's say, from the CT image. But you actually need to know the radioactivity distribution to calculate true scatter. But the whole problem is you're trying to reconstruct the activity distribution in the first place. So how are you going to estimate scatter? You need to know the true activity and the true attenuation map to calculate the amount of scattering. But the whole point of reconstruction is to actually estimate that. So you can sort of imagine that in the same sense as we talked about Chang correction for attenuation in SPEC, where there might be a need for iterative methods, etc., where you first do a reconstruction without scatter correction to get a sort of a rough estimate of the activity distribution, then based on that estimate the scatter, then go back, subtract the scatter, then do another reconstruction kind of approach. So we won't go into details, but at the end of the day, you know, this method, the model-based scatter correction, has been very popular. In SPECT imaging, we mentioned there's like 4 or 5 different methods that have been used, and they're competing methods. In the world of PET, this approach of model-based scatter correction, based on the Klein-Nishina formula, has become pretty dominant, and it's been very effective. And even in the SPEC world, this approach is being taken more and more seriously as SPEC cameras are becoming better and better, because it's a very meticulous and very accurate way of looking at things. So what is the Klein-Nishina formula? And we've seen this before. You know, Carlos has talked about Compton scattering. I've also referred to it in the past. If we know how, you know, if we know how much the incoming photon has scattered by angle-wise, we can calculate how much energy it has retained, right? We know this. But then the question is, okay, sure, if you tell me the angle of scattering, I can tell you how much energy is retained, but what fraction of events are gonna scatter at these different angles? What percentage are gonna scatter at 10 degrees or 20 degrees or 30 degrees or 50 degrees? We need to know that cross-sectional distribution. That's actually what the Klein-Nishina formula does. It estimates the so-called differential cross-section. You know, what is the amount of scattering for different angles? What is the relative contributions? For example, as is plotted here. So these are different energies. And what we care about here is around 511 keV. So this one, so you can sort of see that the majority of, this is that curve here, the majority of events will not scatter. That's good, at 0 degree scattering, so no scattering. But then you're gonna have a fraction of them a fraction of them are going to be, scattered, and it becomes less and less up to here, and then slightly becomes more, so there's a possibility of going all the way 180 degrees. Whereas if you had lower energy photons, there's actually a significant probability of being deflected exactly backwards. Okay. So, yeah. So this allows you to model, how much of scattering happens in different angles, and therefore really calculate the overall scattering profile. We won't go over the math, but just the concept is being mentioned here. Right. Okay. So let's move on to random events. All right. So random events. What are random events? So random events are actually unique to PET imaging. We don't have this issue or challenge in single photon imaging. And they're also called accidental coincidences or just randoms. So this occurs when you have two photons not from the same annihilation event, independent events. They just happen to occur at almost the same time within the timing window of the coincidence processor and the coincidence timing. And they just, one of their events is not detected for some reason. It could be one of multiple reasons, and I'll tell you in a second about that. But let's just imagine one event is detected from here only, and one event is detected from here only, and they happen to be within the same timing window. So the detectors think, well, I got something here, I got something here. They're almost happening at the same time. I'm going to draw a line of response here. And that is totally misleading, as you can see. Now, these singles where the other pair is lost could have happened due to a number of reasons. First of all, it could be that the other pair was never meant to be detected. It was originally headed to leave the scanner anyways. Or it was meant to be detected, but it got scattered away, so it was not detected. Or it just went through the scanner. It just, even though it arrived at the detectors, it was not detected by one of the detectors. And any of these three events can happen. And these could be significant contributions. As we just learned, this kind of this kind of a phenomena, when an event is just lost, is attenuated, is significant in PET, right? Out of, let's say, we sort of said, in that toy example we gave you, out of every 20 events, 19 could be lost due to attenuation. This is an attenuation event. This event was attenuated. It was not detected here due to scattering. So you have a lot of these singles arriving from, let's say, one event here, single, one event here, single, and it puts it together and says, I got a random event here. And that's a problem. Now, you may be wondering, what if the other event was detected, right? What if you got 1, 2, 3, or even 4? So that's called multiple coincidences. That's actually not very common because, as I just mentioned to you, this kind of an event is very, very common where, one of them is detected, the other one is not detected. That actually it happens a lot. But you could have multiple coincidences. Like in this example, I'm showing you one event detected, 2 events detected, and then 3 events detected. Let's say this 4th one was lost due to any of those reasons I mentioned to you. So now you've got 3 events, let's say even 4 events detected. This one's actually not so bad, right? Because if you're getting all these events at the same time, first of all, you cannot really assign an event to that, and you just reject that event. You just reject that event because you got 3 or 4 of them. But if you've got something like this, you don't know that. You don't know that these 2 are from different places. So you're going to count this. This is going to be a random event, a random coincidence. So randoms are unique to PET imaging, as I mentioned to you. Now, the rate of getting such events, let's say along the path from A to B, the line of response along A to B, is actually given by this equation. You can try to convince yourself that this equation is correct, where T is the coincidence timing window. And this is the rate of just singles arriving in here from anywhere. The rate of just getting singles here and the rate of just getting singles here. And if they end up within the same timing window, you're going to get a random event. So you can sort of see this is one reason why having narrower timing windows is better, because as the scanners have gotten, as scintillators have gotten, better, and electronics have gotten faster, you're getting smaller and narrower coincidence timing windows, and that has reduced the random rates, but ultimately you're going to have random rates. Yeah. So as with scatter events, the number of random coincidences detected also depends on the volume of the attenuation characteristics, because it depends on the singles and how much you get singles, depends on all these phenomena. You could even get singles from outside of the body, right? You may have let's say you're imaging your chest, but you got radioactivity from your legs entering the field of view. You don't get true coincidences because you don't get two events from your leg, being detected, but you can get a single event from your leg coming and entering the field of view and adding to the singles rates and potentially therefore resulting in random coincidences with other events that are happening. So it really depends on things like that. And again, just like scatter, random coincidences add statistical noise to the data because you're getting these noisy things, these noisy events added to your signal. Even if you can estimate them on average and subtract them, their noisiness has remained, even though if on average you have corrected for them. So how do you correct for random corrections? Turns out correcting for random corrections is actually one of the easier tasks in PET imaging compared to, for example, scatter correction. This is the way it used to be done. It's kind of a really cool idea. I remember in my PhD studies, this is one of the ideas that was one of the latest concepts that I could finally get into my brain. I just couldn't understand this idea, and it took me a while to figure it out. But basically, the idea is one idea that people used to use especially was this idea of using a delayed window to estimate randoms. So random coincidences tend to, first of all, add a relatively uniform background. A way to correct them is to use the delayed window method. So what is that? So typically, let's just focus on detector 1 and detector 2. Well, if you have a timing window here, it says 12 nanoseconds. The numbers have gotten smaller and smaller and smaller. And because things have become faster, the scintillators have gotten better, the electronics have gotten better. But let's just look at a certain time window. Well, if these two events arrive within a certain time window of each other, we accept them. But what if you introduce this thing called a delayed window, where you say, I'm going to accept an event if detector 1's event is off by like 60 nanoseconds from events from detector number 2. Now, 60 nanoseconds is a large time. That means it's impossible. If you're accepting an event where one of the photons is arriving at this time and one of the photons is arriving 60 nanoseconds later, it's impossible that event is a real true event, right? So it's only, we're looking at only few nanoseconds that you could have within a field of view. So if I'm getting an event now and 60 nanoseconds, I'm getting an event in the other detector, it's impossible these two came from the same event. So that's kind of a really cool way of estimating the effect of randoms, these things that are happening just because two independent events are arriving at a certain time window. So people sort of added this delayed window concept to estimate those events which are impossible to be true events and therefore they're random events. But this approach has had two drawbacks. First of all, this approach itself gives you another noisy estimate to randoms. It's not smooth. It's really another almost like a noisy realization of randoms. And secondly, as you can imagine, it is consuming part of the bandwidth of the scanner. So not only are you now doing your usual timing window, now you're also doing a delayed timing window to estimate the randoms. So you're almost consuming twice as much bandwidth in your coincidence processor. And so these two have been drawbacks, and that's why people have over the years moved away from this technology. Even though it's such a exciting and interesting concept, and whoever thought of it was clearly a genius, but people have moved away from it because of those two problems. So nowadays, people often just use this equation. If I'm measuring, and these things can be measured in PET scans, if I know the rate of singles in each of my detectors, well, I can just use this formula and estimate the rate of randoms. And the nice thing about this is that this is definitely, because the rate of singles, you get a lot of counts, singles in detectors and blocks. These are more smooth. They're not such noisy estimates. So you're getting a nice, smooth estimate of the randoms. So you're not adding extra noise by doing a subtraction. And random rates, because of their square, and notice the square dependence. This is a very key concept. The rate of singles is proportional to the injected dose, but randoms depends on both of these. So it's almost like squared. It is squared. So if you double the injected radioactivity to a patient, the rate of randoms quadruples. Okay. So that is actually, so if you have too high injected doses, that can cause issues. So here are some questions for you guys to try to attempt to answer, to make sure to reinforce the ideas that we've been talking about. Let's move on to dead time, the final part of this first lecture. So dead time effects are also very important things to consider. We have two kinds of dead time phenomena, or kinds of dead time. Paralyzable, when the system is paralyzed, and non-paralyzable when the system is not paralyzed. So imagine you got a system, you got a signal. Just think of like a crystal scintillator. An event comes in. It needs a certain amount of time to process this event. Now, what happens that while it is processing that event, another event comes in? Clearly, during that processing time, it is not available to another event. It does not welcome another event. So that's dead time. But paralyzable is even worse. It says, not only do I not welcome you, but I'm going to penalize you. You have disturbed me, so I'm going to extend my processing time. So I'm going to reject you, and I'm going to penalize even the people coming after you, because you've now extended this kind of processing time. So paralyzable is clearly worse than non-paralyzable. And we have different portions of a system, of a PET system, for example, or a single photon camera, where they're adding to dead time. It could be the scintillators, the detectors, the PMTs, the electronics, the coincidence processor. This is only for PET. And so you could have both of these phenomena. So in a paralyzable, and you guys can work out the math here and these equations on your own. But the point is, as the incoming rate of signal increases, ideally, when you have no losses, the measured signal should just increase linearly. But in practice, for a non-paralyzable system, it starts to detect less and less and less. And this is sort of like the formula. But with a paralyzable system, yeah, it also starts to detect less and less. But at some point, if this rate becomes too high, it totally is paralyzed. It starts to not process anything. It's like anytime a new event comes, it doesn't process and it extends the processing time. So if in extreme case, it's truly paralyzed, like you cannot process anything. So you guys should try to approve these formulas on your own. And in nuclear medicine, we may have a combination of these, like paralyzable, for example, the scintillation detectors, or non-paralyzable, like some electronics. So one of these may be dominant, in which case you just model it as paralyzable or non-paralyzable, or it may be a combination. So you may need a hybrid model to take all those things into account. So here's a question for you guys. Besides radiation safety, what two phenomena limit injection of too much radioactivity into patients? So obviously we cannot inject our patients too much for radiation safety issues, but let's forget about that. Let's say that was not a problem. What are two things that limit how much, or that sort of push you not to inject too much radioactivity into your patients? Attenuation scatter and dead time, attenuation and dead time, randoms and dead time. Which one is it? Yeah, so the answers are coming in, and let's give it like 10 seconds. Think about it. Yeah. So majority of you are saying it correctly. The answer is D. And it's good to remember that phenomena of attenuation and scatter are linear. Basically, it's like fractions. They they do not increase. If you have more, if you double the injected radioactivity to the patient, attenuation percentage doesn't change. Yeah, so besides radiation safety, both randoms and dead time are significant factors, as these are linear. The fractions would be constant. Of course, they would change from patient to patient, but if you double the radioactivity, attenuation does not double. Scatter does not double. Percentage-wise, it remains the same. But randoms, because of that quadratic relationship, it really does increase more percentage-wise. And also dead time just kills more and more events, or at least, especially if it's paralyzable. Even in non-paralyzable, after some point, it's pointless to increase the radioactivity. So to really understand this concept, I want to take you in the next couple of slides to this world of NEC curves or NECR curves. It's a very important concept, which was, again, another one of those concepts that took myself as I was in graduate school to really figure out what it really means. So, and I have a personal memory because I was asked on one of my job interviews after I got my PhD about the NECR curve, and I didn't do such a good job of answering what it really means. So it's always stuck with me. So anyhow, performance characteristics of PET systems. How do I compare one PET scanner with another PET scanner, for example? Or let's say doubling the injected dose versus not doubling the injected dose. How can I compare, given the fact that we just learned if you inject too much, that may not always be advantageous because the randoms and the dead time effects come into the picture. So how do we do that, or how do we look at that? So consider just total counts detected in a scanner, C. And let's say it's a noisy Poisson realization of this. If we kept measuring, we would get this average number. Well, how much is signal to noise ratio? For convenience, we're going to square signal to noise ratio just to make things easier, get rid of some square roots and stuff. So let's just find an equation for signal to noise ratio squared, which is defined as mean of the signal squared, mean of this random variable squared, divided by the standard deviation of this random variable squared, which is the variance. Standard deviation squared is variance, right? So, well, mean, by definition, is this C with this overline squared. Now, we learned in earlier lectures that the variance of a Poisson random variable is equal to its mean. This is a property of Poisson distribution. The variance is equal to the mean. So this is a formula. Now, we don't know the mean. We've only had a single measurement. So our best guess of what the mean is that single measurement. So therefore, our best guess of what the signal to noise ratio squared is this formula, okay? Now, why is that important? Now, let's bring in scattering and randoms and things like that. So what we measure, we tend to call prompt events. It's a mixture of true coincidences and these other, disliked events that have come in, the scattering and the randoms. All these are Poisson. The randoms are Poisson. Scatter are Poisson measurements. True coincidences are that. And therefore, this total count itself is also. So these are all random variables. And just think of it as Poisson distributed random variable. This is what we are measuring. When we measure total counts in a PET scanner, this is what we're measuring. But we know a part of that is scatter, part of that is randoms. So to estimate the true number of counts, or counts coming from the true coincidence as well, we're going to have to estimate the scatter and the random counts. Well, let's say we have a really nice way of estimating the scattering. And let's say it's a smooth estimate. It's a nicely average estimate, so it's not really noisy. And for randoms too, let's say we're using this second approach that I showed you that is not like the delayed coincidence window where it's a noisy estimate itself, it's a smooth estimate. So we have nice smooth estimates. And you might be thinking, well, great, we're done. We're just going to subtract these from the prompts and we're going to get the estimated truth using this formula. This is what we measured, the P, and we're going to get this. Okay, so but how much is the signal to noise ratio squared? Going back to that same formula, what is the mean of this squared and what is the variance of this? Well, if you take the mean of this formula, remember, these are already means of these. These ones cancel out. The mean, put an overline on T, overline on S, overline on R. These already have overlines, so these cancel out when you take the mean. You're just left with this term. For the variance, however, you cannot do that because variance of A plus B plus C turns out to be equal to the variance of each one of them summed up. But the variance of T is T with an overline. Variance of S is that. And variance of R is that. Remember this formula here? Variance is equal to the mean. But these ones are already average terms, so they don't have a variance, presumably, right? So notice what just happened. You have corrected by the subtraction the mean value. So you have a nice mean value, but you cannot get rid of the noisy contributions of scatter randoms. Scatter randoms already added noise to your signal. So even if you subtract them on average by a nice smooth estimate, still the noise they contributed stays there. And since we only have a single realization of each of these, just like here when we estimated this term by that term, we can do a similar thing here. This is our best guess. But notice, the more scatter randoms that you get, even though you're subtracting for them, but the noise effect stays with you. So it's not good to have so much scatter randoms. It degrades the quality of your image. It degrades your signal to noise ratio. So this signal to noise ratio square term, that's actually what people are referring to as so-called noise equivalent counting rate. It's the same thing, okay? And it is in a sense a measure of effective count rate taking noise degrading impact of scatter random into account. So imagine if S and R were 0, if you had no scattering, no randoms, well, then you just reduce to, Poisson statistics of a pure clean signal. But because of these two events, the effective count rate sort of is degraded. This number reduces. So how is this used in practice? Look at these curves. Imagine that you are measuring a phantom, for example, that is decaying over time. You start with really high activity or single rates, and you see how it declines over time. We do this in the lab, for example. We start with a really high activity phantom, let it decay over hours and hours, and just measure how many true counts do we get? How much scattering do we get? How much randoms do we get, for example, right? And when you use that formula that we had here and you plug it in, that gives you the NEC curve. Now look at this amazing curve. This curve tells you that too much activity is bad because NEC curve comes down. Too much activity is bad. Why? Because this randoms is totally dominating. And also by this time, the true counts have gone down because the dead time is starting to dominate. This is not going up linearly. Dead time is hitting this one, for example. And also randoms are totally dominating. So there's this intermediate, injected radioactivity that is optimal. You don't want to inject too little. You don't want to inject too much. And this also allows you to compare different kinds of scanners. This is just a very qualitative figure I drew years ago, where I was trying to just convey, what are the differences between these different scanners. So as you switch from BGO to LSO crystals, you're getting higher photon yield. You're having, faster scintillators, less dead time, improve coincidence detection. You're just getting better NEC curves. And when people used to use SEPTA and 2D imaging, you had to inject a lot of activity into the patient to get to the peak of this. And that might have conflicted with radiation safety issues. So in practice, people were already here because of radiation safety considerations anyways. So if you're already here, 3D clearly has an advantage. You can actually and really in practice, we're now here. You can inject now far less. I remember when I was at Johns Hopkins University, we used to inject 20 millicuries into our patients routinely. Now that numbers has dropped to 10 millicuries and less, because you could be just injecting around in here and get really superb uptake. Whereas with those low doses, you would not have in 2D, and nobody really goes that high for 2D because then this might conflict with radiation safety issues. So that's one reason people have switched to 3D. And these curves have improved, by the way. These curves have improved and improved over the years. So that's why people have gradually switched to 3D imaging and to LSO crystals, though there are BGO cameras because of more affordability that are still out there, and they're very good cameras too. So the NECR curve provides an estimate of the range of activities within which best image qualities are expected to be obtained. And it also helps with comparison of different scanners and generations of scanners. If you compare like NECR curves between a previous generation, new generation scanner, you will see like improved numbers. Numbers increase, and sometimes the peak is maximized at different radioactivities. But ultimately, this is a rough estimate. It's just purely based on like counts and total counts. And image quality has to be really assessed carefully. You really, at the end of the day, we look at these numbers as physicists, but we really have to, and the radiologists really have to, and they do go through images and take other aspects into consideration when decisions are made, for example, about whether to purchase a certain kind of camera or which kind of reconstruction algorithm, obviously, because reconstruction algorithm changes image performance, whereas, here, these are just total counts. We're not taking the effect of reconstruction and things of the sort into account. So we covered these 4, and in our next lecture, we will cover the next 4 phenomena that degrade PET images.